Hello everyone. In this video, I was planning to discuss an INMO problem from this year 2026 P2. So this problem was relatively easy when compared to the others. Let's have a look. You are given with a function from natural numbers to natural numbers that represents maximum number of times a certain number is repeated in the sequence. They are starting from k greater than 2026. So the function definition starts from 2027. So all the functional values before that are assumed to be something. So for example, let's take the values of x as 1, 2, 3 up to 2026. The functional values at those points to be a1, a2, a3 up to a 2026. Now from 2027 onwards, you are going to write the maximum number of times a particular number in this list gets repeated. Now for 2028, you do the same, just including 2027. The functional values from f of 1 to f of 2027 are analyzed, and the number of times a particular number is repeated is written as the functional value for f 2028. Now we are asked to prove that f of n equals f of n plus f of n for infinitely many n's. Not for all n, this in fact will not be true for all n. They are asking us to prove this for infinitely many values of n. Infinitely many n. So first let's analyze how the functional value looks like, and later on we will make some inferences and we will comment on this. So at first, notice that the function will not have an upper bound. So if you keep on enumerating the list, you will see that the values are not bounded above by some number. They will exceed any given natural number value or real number value. That's the meaning of unbounded. It grows unboundedly. What's the reason behind this? For the sake of contradiction, assume that there is an upper bound capital N. Let capital N be an upper bound. That means all the functional values up to any value cannot exceed n. It can equal n, but it cannot exceed n. So all the entries are less than or equal to n. We will work on this and derive a contradiction. Therefore, there is no upper bound and it grows unboundedly. Clearly, the values that can occur in the range in the sense values of f of x. So values of f of x can be 1, 2 or 3 or 4 up to n, and each of them occurs at most n times. So this is the frequency that I am representing, the frequency of a particular value in the range of the function f. So this is the frequency that we are enumerating for each of the values from 1 to n. We do not know the exact value, but the frequency is bounded above by capital N. If suppose some of them occurred more than capital N times, then you must have a value of the number of occurrences of that number, because that is now greater than n. So the maximum number will be greater than n, which contradicts our n being an upper bound. So we will assume that without loss of generality, the frequency of each number is less than or equal to n. Now notice, if each number occurs in the range, in the enumeration of the range at most n times, and there are total n numbers, so you will have n times n numbers at most. And thereby you can see something is going wrong. We have infinitely many numbers here, but here you are just having n square numbers possible. What if you take the first n square plus 1 number. You will get that one of these will be greater than capital N. Thereby, an upper bound clearly gives a contradiction. So, due to which we will assume that there is no upper bound for f of x. Or you can also say that f of x grows unboundedly. So what next? Let's understand our requirement. The question asks f of n equal f of n plus f of n. So this means f of n occurred as a value at n, and it also occurred at n plus f of n. This means the maximum number of times a value occurred before n was f of n times. And that is even same as the number of times a value occurred before n plus f of n. So the maximum number of times a particular value occurred is still f of n. Once you cross all these, like from n to n plus f of n, you are still having that same number, the maximum number of times or frequency of a number retained. So this means all these values must also be f of n, because this value itself is f of n. And if you take a value before this, you are analyzing a subset of that. So for n plus f of n, you should analyze all the numbers from 1, the number for n plus f of n, you should analyze all the functional values from 1 to n plus f of n minus 1. Now when you think about n plus f of n minus 1, you should analyze all values, functional values from 1 taken at 1 to n plus f of n minus 2, which is a subset of the earlier analysis. Therefore, the maximum number of times that it occurred will not be greater than f of n. So it will be at most f of n, and it will be equal to f of n because at n it is already reaching f of n. So even here it will be f of n. Therefore, all the values from n to n plus f of n are all f of n. So in fact, let's see what the requirement says. So there are certain numbers from 1 to n minus 1, and the functional values are there, like f of 1 up to f of n minus 1. Now from n, you have f of n, and at n plus 1, n plus 2, so on up to n plus f of n, all these values are f of n. This is exactly what our question's requirement poses us. We want such a scenario, and that too occurring infinitely many times. You see, this is f of n by definition, and they require this also as f of n, and I know this functional values are non-decreasing. So the next value will also be f of n, because ultimately it is reaching f of n here at n plus f of n. So all these values cannot exceed f of n, and of course it cannot decrease further because you are having f of n frequency already. So you cannot have something less than f of n frequency after analyzing n, because now you are analyzing a superset of what you analyze for n. Now if this is the scenario, notice that a number, what does this signify? A number repeated f of n times, and that is the maximum frequency. But now here you have f of n repeated how many times? F of n from n to n plus f of n. Totally there are f of n plus 1 terms. Therefore, f of n itself repeated f of n plus 1 times. So therefore, you cannot have a f of n here, and you should not have, because if it were, if f of n were to occur before, then you will have, if it occurs at least once before, you will have before n plus f of n, that f of n occurred f of n plus 1 times. So we cannot have f of n to occur before the value n. So take some new value, that means some value that occurred for the first time in the range of f up to n, and from there on this will be clearly possible because f of n occurred no time before. So up to n plus f of n minus 1, f of n occurred f of n times, so clearly this entry will also be f of n. So we just have to seek for some term that occurred for the very first time, and we will start from there, go up to f of n times, and prove that there are infinitely many new numbers introduced in the range. And due to this unboundedness, it's clear that such a value exists. So take x and f of x. You have some values up to 20, 26. Say they are a1, a2 as before, up to a20, 26. So take these numbers and calculate the maximum. Let's say it's at most capital M. Now, since the range is unbounded, you will reach some value greater than m. Let's call it as m prime. And let's assume that it occurs at small m prime for the very first time, because up to 2026 terms, m prime did not occur, and m prime is a number greater than m. Such a number will occur somewhere because the sequence is unbounded. Therefore, we assume that it occurs at m prime for the very first time, and then thereon it will occur exactly m prime times. So that is m prime plus the small m prime plus capital M prime's entry will also be capital M prime, because up to this point m prime occurred only m prime times. So the maximum times will be m prime still. So therefore, you get that f of m prime equal f of m prime plus capital M prime, but capital M prime can be replaced with small m prime, f of small m prime. And hence we have showed that such a value of m prime exists. But how to show that it exists infinitely? Well, now just consider all the values here and assume its maximum to be m double prime, and then find some value greater than that, m triple prime, take its first occurrence, and then go capital M triple prime times into the sequence, and you will see it for yourself infinitely. So you can also prove it via contradiction. Suppose it occurs only finitely many times, then the sequence grows unboundedly, leading to a contradiction. This is how you can solve this. First, the intuition should not be to write it stepwise. The intuition should be for yourself to understand what's the meaning of the given functional equation. Well, it just means that f of n occurs f of n times or f of n plus 1 times in the sequence. So after realizing this pattern, you have to see what numbers satisfy this property. So newly generated numbers shall satisfy this. If it's not newly generated, it cannot have so many numbers occur. So after this analysis, you can write the proof by yourself. Alright. If you have any other ideas or suggestions, please feel free to put in the comment box. We will meet in the next video. Thank you everyone. Bye.